When I was taking Gen Phys 1, it was very clear to me how the class could be useful, but I always found it a bit unsatisfying because it seemed like we were memorizing equations for specific and sort of random systems that we were taught in class. It didn't really feel like this knowledge could generalize to a system I hadn't seen before. It turns out that all of General Physics 1 is derived from a slightly more fundamental model of how the world works, which we call the principle of least action, and I'll do my best to explain my understanding of it here. Here's the key equation. I still don't have great intuition for why this is true, but I'll try to give intuition for what it means. The first part of the expression to look at is this inside part. Here, T represents the kinetic energy and U represents the potential energy. I know T is a little bit of a weird letter to represent kinetic energy, but this is just the convention we had in my analytical mechanics class. T and U are both functions of time, so all this term is the instantaneous difference between kinetic and potential energy. In analytical mechanics, they call this the Lagrangian, and they use the letter L for it. We can get the total action by integrating our instantaneous kinetic and potential energy difference over time. So our kinetic and potential energy difference is sort of like the action density over time. Bear with me for a bit. This may seem like a more complicated way to do physics than just looking at the forces, but it will turn out to give us something really useful. Kinetic and potential energy depend on the path the object takes. For instance, if we were to consider dropping a ball in a uniform gravitational field, the potential energy depends directly on the height, and the kinetic energy depends on the velocity, or the time derivative of height. So, given a path, any arbitrary path, we can calculate the potential and kinetic energy and integrate it over time to find the action corresponding to that path, even if that's a path you would never see the ball take in the real world. It turns out that the path that you actually observe the ball taking in the real world is the path which corresponds to the least action. To make this a bit more intuitive, let's go back to our ball example and try to visualize the action for a particular path. Here, the y-axis represents height and the x-axis represents time. We'll choose the arbitrary boundary conditions that the height is 0 at t equals 0 and 0 at t equals 1. This means we can consider any function that satisfies these boundary conditions. We'll draw a squiggly line to represent all possible functions that satisfy those boundary conditions. Every frame of this is a random path that you would never see the particle take in reality, but we can still calculate the potential and kinetic energy over time corresponding to any of these paths. For the sake of visualizing the action, let's consider a simpler path. We know the potential is a function of height. This potential function looks exactly like how we'd expect it to, since the potential is just proportional to the height. We can also work out the kinetic energy and plot that. The action for this path visually looks like the area between the potential and kinetic energy curves between the fixed endpoints of the path. Nature, for some reason that I don't have great intuition for, tends to minimize this area. So, given that you have a particle in a uniform gravitational field that's at height 0 at t equals 0 and height 0 at t equals 1 without any normal force from a surface, the orange line is the path that the particle will actually take. And this path should sort of be consistent with your intuition. The particle must have some initial velocity upward in order to satisfy the boundary conditions and fall back down to where it was before. Let's rescale the axes so it's a bit easier to look at. And then I'll create a ball, and I'll animate one ball going over the path through time, and then I'll animate another ball not moving on the x-axis, so it will just look like how it would look in the real world, because there's only a y component to our velocity. Even without intuition for why nature minimizes action, we can still take advantage of this knowledge to figure out how a system would evolve over time. Now, this is a nice idea, but it's useless unless we actually have a way of arriving at an optimal trajectory for a given Lagrangian, or the trajectory of least action. So I'll talk about one last new piece of math that might be unfamiliar to someone who hasn't dealt with calculus of variations. This is called the Euler-Lagrange equation. The problem we're trying to solve is an optimization problem, although it's a weird optimization problem because instead of finding a point that maximizes or minimizes our function, we're finding a function that minimizes or maximizes the integral of the Lagrangian. Euler's equation is a tool that's designed specifically for this type of problem. Also, in the example I showed, we applied boundary conditions to get a specific solution, but Euler's equation is more general and will give us a family of functions to which we can apply boundary conditions afterward. This might make a little more sense after doing an example, but before we do that, there's one important thing to note. Since the Lagrangian usually depends on position and velocity, it's important to know how to take the derivative of position with respect to velocity, or vice versa. When I saw this last semester in analytical mechanics, I was kind of confused because it seemed like y and y prime should be dependent. I guess it turns out that my math here is flawed because in the context of calculus of variations, we don't yet know the path that the particle takes. So At any given point, regardless of the position, the velocity could be anything, so we can treat them as independent variables. This, again, is because we don't yet know the whole path, and we can't derive velocity from our knowledge of position at any individual given point. With that out of the way, we now know enough to be able to use Euler's equation to find the path that minimizes the action. If we wanted to solve our ball dropping example, we could start by writing our kinetic and potential energy expressions and find their difference to get our Lagrangian. Now we have our Lagrangian, and remember, our task is to find what position function will minimize our action. So we need to find a function that we can plug in for h to minimize the integral. We can find our h as a function of t by plugging L into Euler's equation. And now it's just a matter of taking derivatives and doing algebra. I usually start by evaluating partial of L with respect to h and with respect to h dot, and then I can just do the time derivative of partial L partial h dot. Then we no longer need partial L partial h dot, so we can get rid of that, and the remaining two parts are all we need for our Euler's equation. Substituting what we just solved for back into Euler's equation gives us a differential equation, and if we solve it for h, it will give us the path the particle takes over time. This particular differential equation is pretty straightforward. We just integrate twice over time. Notice, this equation looks a lot like one of the kinematic equations you might have seen if you took General Physics 1. What's nice about this approach is that even though it can seem a bit less intuitive at first, it generalizes well, and you can derive how a system would function that you haven't seen before. In Physics 1, we were just told a sort of random model for a pendulum, but suppose we didn't know that. Could we derive it? This looks like a system that might be well suited for polar coordinates, so we'll use that and we'll try to figure out how theta varies with time. The length of the right side of this triangle is just going to be L cosine theta, and since we set y equal to 0 right at the top, it's in the negative direction. So y, or the height, is negative L cosine theta. To get our velocity, we can look up what ds is in terms of dr and d theta, where ds just represents some infinitesimally small change in any direction. We can ignore the dr component because the length of our pendulum isn't going to change, and our velocity is going to be an infinitesimally small change in position over an infinitesimally small change in time. So if we, I guess, sort of divide everything by dt, then that will give us our velocity. And from this point on, it's pretty straightforward. We have our potential and kinetic energy, so we can take their difference to get our Lagrangian, and then plug that into Euler's formula, and then it's just a matter of taking derivatives. This differential equation is our solution, and if you're taught the solution, you might be wondering why this doesn't look familiar. And that's because the equation you were probably taught isn't technically correct. If you were ever wondering why it was only valid for small angles, well, this is why. If we're only interested in getting a small angle approximation, then we can use something called perturbation method and substitute in a first-order approximation for sine of theta, which makes this differential equation easier to solve. Although this is easier to solve, it's now only valid for small angles. And after some simplifying, we arrive at our small angle approximation for theta as a function of time. So we were able to derive a couple of models that are used in General Physics 1, but we're also able to figure out how really weird systems like a bead on a parabolic spinning wire would act. You might expect that in a system like this, you'd have some fake centrifugal force pushing the bead out, and it would be counteracted by gravity pushing it down, and there would be some stable equilibrium somewhere. And it turns out for most wires, that's true. The parabolic wire is sort of a special shape in that when you're spinning at just the right speed, anywhere on the wire is an equally stable equilibrium. This is an example of a system that would be extremely hard to solve with just the knowledge of forces from General Physics 1, but with Lagrangian Dynamics this actually becomes doable. For this setup, we'll let ρ be this orange vector and represent the distance from the z-axis to the bead, and we'll let phi represent the angle of the parabola from the x-axis. It isn't trivial to find the velocity, so we'll write x, y, and z in terms of phi and ρ. From that we can take the time derivatives of x, y, and z, and then find the square of the time derivatives of x, y, and z. This is useful because we can define the velocity in terms of the squares of the time derivatives of x, y, and z. This is just Pythagorean theorem. The magnitude of velocity squared equals the sum of the square of each of its components. We can substitute in what we found for x, y, and z dot, and then figure out what the velocity is. After some simplifying, we get a pretty reasonable expression for velocity in terms of ρ and phi. Now that we have velocity and z, we can figure out our t and our u values pretty easily. Our kinetic energy is just going to be 1/2 mv squared, and our potential energy is just our gravitational potential energy expression, mg and then times the height. As with all previous examples, we can find L by subtracting t and u, and then from here it's pretty straightforward. It's just a matter of doing derivatives and algebra. And that's our equation of motion. This differential equation's not trivial, so we can find our equilibrium positions by just finding where p dot and p double dot are 0. What this is telling us is that when omega, which is the angular velocity of the parabolic wire, equals root 2gk, then our system is at an equilibrium. And notice that doesn't depend at all on rho. This means that as long as our parabolic wire is spinning at that angular velocity, our bead position could be anything and it would just stay there. Personally, I thought Lagrangian Dynamics was a lot more satisfying than General Physics 1 because it can be applied to crazy systems, and this multi-pendulum can actually be solved using Lagrangian Dynamics, although it's not solvable analytically. We can still use Lagrangian Dynamics to arrive at an equation of motion for the system, but we would need a numeric solver in order to get what it looks like. Anyway, I hope that this was an entertaining and interesting video for you, and hopefully it's useful if this is something you need to know.